Okay. Okay. So we did many homework assignment problems last time. So today we're mostly going to talk about material that is not related with the midterm, except if you have questions about this.
Are you going to do like a study?
Oh, yes. So in the previous section, we agreed to have the study, actually they asked me to have the study session on Monday after class, which means at noon on Monday before this class. But again, I'm not going to solve any problem that you don't ask for. So you have to go over the practice test, homework, any possible problem, and ask for a problem to be solved. Otherwise, there are so many problems that yeah.
Will there be like one of those tests that has like a specific problem that we could study for, like the last one?
Well, all versions are going to, I think, maybe I have to sit down and write, but I intend to ask for all versions of the test. I intend to ask image formation either by a lens or by a mirror, but you have to draw the diagram well. And the diagram is going to be the main part of the problem. So all versions I'm going to ask people to do different positions of the object with respect to the lens or the mirror, and describe, so draw correctly the diagram and describe the properties of the image. Real or virtual, enlarged or reduced in size, or upright and or image. So those are good. So this is one type of questions. If you're going to have questions also, all versions are going to have questions about the human eye. So eyeglasses in the human eye, and going is the near point, or the near point is this, where do you have to put the questions of that type. If you look at the homework assignment, there are many questions like this. And also in the practice test, there are many questions of that type. All of those questions need the diagram. But of course, the diagram for image formation by lenses mirrors is different from the diagram that you need for, let's say, determining the focal length of eyeglasses for farsighted person. Right? It's going to be, again, I'll try to put questions that require substance rather than arithmetic technical details. But while the substance is very often in diagrams, and you need to know the sign convention in order to get it right for the calculational problems. Okay, other issues, questions, remarks? No? It is Friday, and it is still relatively good attendance today. Right, well, there should be something wrong with person that comes to class in state of 70 degrees outside, right? That's where everything. And I appreciate it. So look, a simple way to visualize the interference pattern for the case of light waves, light or sound waves, or any other waves is with this simple transparency. So this transparency, you have a point-like source that uniformly emits waves in all directions. And those waves, again, could be light, or it could be sound waves or something else. And the black lines, let's say, represent the wave fronts. And the wavefront, let's say, where at certain moment of time, let's say you have the highest light intensity at certain moment of time. Of course, those circles are propagating, they are increasing their radius with the speed of light. And if you have a second light source of the same type, the same wavelength, and in coherent with the first source. And if they work simultaneously, you see that this picture. This picture indicates that at places where two dark wavefronts are on top of each other, you're going to have high intensity of the light. And at places where you have white wavefront on top of dark wavefront, you're going to have destructive interference there, and therefore dark spot. And of course, you're going to jump and say, well, here is one light source, here is another light source. Why can't I find dark spots anywhere in this front? Why don't I see this interference pattern? What do you say? Many reasons, of course. So, well, the trick is that in order to be able to observe interference pattern, several conditions have to be satisfied. The two waves have to be with the same wavelength. One single wavelength where, well, our light sources here are all visible wavelengths are represented there. So this is one reason. The second reason is that the two sources have to emit coherent light. Coherent meaning that the phase difference between the light emitted by the first and the second has to be a constant phase difference. Let's say they could be exactly in sync, exactly in phase, or they may differ by 30 degrees or by 90 degrees or by 180 degrees. But that difference of the two phases have to be constant. And well, it is difficult to make two different sources of light to be coherent. The way to make it a coherent, two sources to be coherent, is to take a single small size source of monochromatic light, which could be even a fluorescent light like this, and you just filter out, let's say, leave only the blue or leave only the red. And after that, to make it coherent, so the filter, the color filter is going to make it monochromatic, a single wavelength. And after that, to make the single wavelength coherent, you can pass that light source through a narrow spot. And the result is going to be more or less coherent light on the other side of the narrow opening. And of course, you wait. Once you have a coherent source after this narrow opening, you can split it into two with two other openings after that, and let the light that goes through those two narrow openings to interfere. And what you're going to see, we saw it last time. So here, two slots. I have a coherent source of light. Laser light happens to be coherent. I don't need to make it coherent with a preliminary narrow slit. And here are two relatively closely separated slits. And you see that instead of seeing two projections of those two slits, you see a single central bright spot. A single central bright spot. And after that, a sequence of dark and bright secondary light. The same thing with the different, let's see. So this is different separation between the two slits. Last time we brought the formula for the condition for destructive and constructive interference. The spots that are bright are the place where you have constructive interference between the light that comes from the left and from the right slit. And the dark spots are the places where you have destructive interference of the light rays that come from the left and from the right slit. Last time we also talked about the fact that you observe a similar interference pattern if the light goes through a single slit, through a single opening. Pretty much very similar interference pattern. Let's select one. Here it is. So this is a single narrow opening, and you see the sequence of bright and dark spots around the central bright spot. And this phenomenon, a sequence of bright and dark spots after a single opening, is what we call diffraction of light, or any other ways. Diffraction pattern is what you observe. And we proved that if you have a single slit, a single opening with a width W, and if you have here coming in monochromatic light, far from that single slit, a long distance after the single slit on a screen, we said, and you saw it, you observe a central bright maximum, followed by a dark and secondary maxima after that, like this. What we proved was the location of the first dark spot. And we found that the first dark spot is going to appear at an angle with respect to the central line, an angle theta. So here is the angle theta that satisfies the following condition. Sine of the angle theta is equal to lambda divided by the width of the slit. Lambda is the wavelength, of course, of the monochromatic incoming light. Well, if instead of rectangular shaped slit, you have a circular opening with a diameter D, capital D, you have a similar diffraction pattern for the light that comes in through this opening. The only difference is that the angle at which the first dark spot appears is 1.22 times lambda, and instead of the width of the slit, you have the diameter D of the opening, the diameter T of the opening. Yes. And this is useful and important because everything that we see, usually we see through a circular openings, right? Your eye, the pupil of your eye is circular opening. And when you're looking at the world, or when you, well, for simplicity, when you're looking at a single point-like source of light, maybe a single light bulb source of monochromatic coherent light, on your retina here, you're seeing that single source as a bright spot in your retina formed. But around that bright spot, you have a sequence of bright circles and dark circles. You see, there is an interference pattern, and if you're careful, you can see it under certain conditions. Depending upon what is the diameter of the pupil, what is the diameter of the circular opening, the resolving power of your eye is going to be different. So in general, larger opening, larger enlarged pupil, dilated eye is going to have more resolving power. So, and we're going to encounter problems where you have to calculate exactly the resolving power. By resolving power, meaning how far two objects could be from each other and how far the observer, you, could be to see those two objects as separate objects, or they're going to blend together and you're going to see them as single one. This is what the resolving power is, and we're going to encounter quite a number of questions related with resolving power of the human eye and resolving power of the difficult, well, telescopes, microscopes, and other optical instruments. All of them are going to rely on the second formula, which is quite simple.
One more time, where did the 1.22 come from?
The origin of the number 1.22, we cannot, so it requires quite complicated mathematics to get this number, to prove it mathematically. So in your textbook, of course, it's not, this derivation is not shown, and you're not going to just remember the results. So this 1.22 comes from the fact that instead of having a rectangular slit that we analyzed already, you have a circular opening. So this is the origin of, and if you want to figure out exactly how to obtain this 1.22 number and maybe get more significant digits after that, you know the price that you have to pay, right? Everybody knows it, right? What is the price? No, it's exactly the opposite.
Format.
No, it is exactly the opposite. It is actually a quite pleasant experience. The price that you have to pay is you have to switch to a physics major and enjoy the okay. Now look, what is surprising is that if instead of an opening, you have a barrier of light for light, so some non-transparent small barrier with circular shape or with a rectangular shape. you observe exactly the same diffraction pattern after it. This is what is strange, but it is experimental fact. In a sense, when I showed you the two-slit interference pattern here, one slit separated by, in a sense, the interference pattern that you observe here could be interpreted as if it is generated by this barrier. Like the light comes in here, and you observe the interference pattern. So this is one easy way to think about the fact that diffraction and interference are pretty much the same sides or two sides of the same coin, let's say. Now, I don't want to solve examples related with interference and diffraction at this point, because chapter 27 is not going to be part of our midterm. And I don't want you to be confused, but this chapter 27, interference, diffraction of light, is important. And it is, of course, going to be on the final, which, well, we have some time until the final exam. And the homework assignment has multiple problems related with this. Now, yes.
How many more chapters do we have?
So the textbook has 32 chapters total. And since in the first semester, we did 17 chapters in the first semester. So what is left this semester is 15 chapters, which is up to chapter 32. So what I usually don't want to do is to cover the chapter on relativity. This is chapter 28 on special relativity, because it is going to be something that practically, well, you have some practical applications for that if you're designing, let's say, GPS system or something of that. But otherwise, the practical applications are quite limited of special relativity, general relativity too. And also, it could be quite confusing experience. So chapter 28 is probably going to be out, maybe at the end of the semester, maybe the last class I can talk about relativity, special relativity, general relativity, but I'm not going to ask any questions in the final exam about it, just to give you a general idea. So usually the chapters after chapter 27 are classified as modern physics, and usually in other schools they're separate course. That separate course includes introduction to quantum mechanics, introduction to special relativity, introduction to nuclear and particle physics. But here we're going to be able to talk about basic concepts of quantum mechanics. This is chapter 29. And a little bit of nuclear and particle physics. This is chapter 30, 31, and chapter 32. I don't remember what it was. But it is again, probably it is a mixture of conceptual quantum mechanics with particle physics and some discussion of general ideas in modern physics. So the emphasis on the final exam is going to be on the material that we're covering now: electromagnetic waves, optics, geometric, and interference diffraction. And I'm going to have several questions related with, well, maybe some hydrogen atom questions, very conceptual, which is chapter 2030. Okay. And all those questions are going to be in a simple and in a context of practical applications. And the homework assignment problems are going to be of that type, not some complicated, very abstract ideas. It's going to be something very specific. Okay, other questions, remarks? Now, before I go to some conceptual questions related with interference and diffraction of light, let me give you one simple formula that's going to be useful when you're talking about interference and diffraction, interference especially from thin films. Let's say that you have the surface of water, let's say. In other words, on this side, you have air with index of refraction n1 equal to 1. And on this side, you have some transparent material. Could be water, could be some other material with index of refraction, let's say 1.33. What matters is that the second material has higher index of refraction. And the question is, if you have a monochromatic light coming in here with wavelength lambda, the light ray that enters the second material is going to have a different wavelength, different color, even though the material may be completely transparent and not colored material. So the question is, what is going to be this different color? What is the wavelength of light if you, as an observer, see it right here? And we can easily calculate that wavelength. So look, the wavelength lambda prime, by definition, is proportional to the speed of light in that material divided by the frequency of the light. So what I want you to remember and keep in mind is that no matter where the light propagates, the frequency doesn't change. Whatever is the frequency in this material, exactly the same frequency you have in the second material. The frequency cannot change. So this is the wavelength in the second material. And if I divide numerator and denominator of this expression to the speed of light in vacuum, so here just divide this to the speed of light in vacuum, divide this also to the speed of light in vacuum. Nothing changes, right? Up here, what do you have up here? Up here is the inverse of the index of refraction of the second material. Remember, by definition, index of refraction is the speed of light divided by, in vacuum, divided by the speed of light in your material. So the inverse is the inverse of the index of refraction. What we have here, well, you can say that the inverse of frequency is the period of oscillations. So you can say that this is 1 divided by the period of oscillation multiplied by the speed of light. And this expression here is exactly the wavelength of your light in the first material, in air. In other words, you have 1 over n2 divided by 1 over the wavelength of light in air or vacuum. And of course, when you rearrange this fraction, you get that this is lambda divided by n2. So again, I played around with arithmetic. You don't need to remember how to derive this, but the result is needed. The result says that as the light enters optically slower material, its color, its wavelength changes. Its wavelength shrinks proportional to the index of refraction of the second material where you enter. So basically, where you're underwater and the water is completely white and not white, but completely transparent water, and you look above, you're going to detect the shift of all colors to the blue part of the spectrum, shorter wavelengths. And this actually matters because of the formula, let's say, for you're going to see examples when we do examples from for chapter 27. But basically, when you're looking at incoming light with your eye is nothing else but a transparent medium with index of refraction that is larger even than the index of refraction of water. So if you're looking at a single color light, red, what enters your eye and hits the retina is going to be shifted a little bit to the blue part of the spectrum. It is still going to be red, but not. It's going to be a little bit more shorter wavelength than what comes in. And as a result, you're going to see that the resolving power of your eye is going to improve a little bit as you because of the formula for resolving power. Yes.
So somebody with like an abnormally high index of reflection in their eye, would they be like colorblind?
Actually, color blindness is due to completely biological reasons rather than to simple physics. And biology, of course, is more complicated than physics, even though physics is more interesting. Yes, yes.
Not a bias, you know.
Yeah. So, but no bias. But yeah, some of you are taking anatomy and physiology classes, so you know that the photosensitive cells in the retina, those that you use during the daylight for color vision, are 3 types, and the 3 types are sensitive either to red or to blue or green, I guess. And if one of the cell types is missing, or it is not in the numbers that it should be, or it just doesn't, one of the types doesn't work properly, you lose your ability to detect that particular color to one extent or to others. So color blindness mostly impacts males, but it sometimes happens in females also. And actually, it is more common than people may assume. It occurs quite often. I don't know the numbers, but it happens. Okay, other device questions? Okay, so let me, so we have time. Again, I don't want to do calculational problems that are related with material that's not going to be on the test that is coming. So let's just, for the fun of it, let's look at some conceptual questions rather than calculational questions. And when we finish the conceptual questions that I have, we can do some calculational problems just to help with the material that is coming next week. Oops. Ooh. Did I show the answer there? What do you say? What? So coherence is a tricky concept to understand because we haven't talked in detail about the phase of a wave. But, well, the phase difference of the wave emitted by the light of the light emitted by the two sources has to be constant phase difference. So you have let's go to the next one. So here are two light sources, and both of them are lasers. Therefore, this is coherent, this is coherent. And if I try to, if I try to put them on the same spot, believe me, you're not going to see that interference pattern because it doesn't happen. For the case of lasers, you don't see interference pattern, even though the two sources are coherent. You don't see the interference pattern. Why? To lasers. Different wavelength. They're different wavelength. This one is green, this one is blue. You need the same wavelength to see the interference pattern. But for this case, well, look, if the intensity of the two waves are different, if intensities are different, but the two waves have the same wavelength and they're coherent, you're still going to see interference pattern, but instead of a dark spot, you're going to see a spot that is not so bright. That's it. It is still going to be an interference pattern, but not so nicely visible with completely dark spots. Ordinary light sources are not coherent. Sources are not coherent sources of coherent light. And the reason is very simple. The reason is that the light that is emitted by this part of the fluorescent light right there is emitted by an atom or a molecule that is located there. While the light emitted from the other end of the light bulb is emitted by a completely different atom that doesn't know anything about the atom that is separated from it. Doesn't know anything about it, and it cannot be in sync with that atom because they don't know about each other. Well, in order to make that light coherent, you have to either shrink the size of the fluorescent light, or you have to take an opening, a small opening that only separates only the light from one, almost a single atom. And then you're going to get coherent light. It has to be monochromatic, so first you have to pass it through a filter to separate the single color. Okay, let's see the next question. So this question is a little bit not because they're asking about the convincing evidence that light is electromagnetic wave. So whatever is convincing for you may not be convincing for you, right? It is very well, but so coherence of light related with electromagnetic wave, probably not quite. Reflection, well, you have reflection not only of waves, but any other object is reflected here. It is this piece of, what is it?
Tape.
Yeah, this tape is reflected from table. This doesn't mean that this is electromagnetic wave. The light can form double-slit interference pattern. Can you form double-slit interference pattern? So well, if you're having a stream of particles, can you or you cannot? A stream of particles that hits double slits. Are you going to form interference pattern of the type that you see with light? There is no actually, well, no matter what you say, it is going to be right. Because actually, well, we're going to talk about wave nature of objects. But surprisingly, even material objects under appropriate conditions form interference pattern. So you had chemistry, and one of the relatively recent experiments was a stream of those buckyballs, those carbon molecules with 90 or more atoms put together. So they're relatively large molecules, 90, more than 90 atoms, 100 atoms. And you pass a stream of those buckyballs through two slits, and on the other side on the screen, you observe interference pattern. But in classical physics, interference pattern is thought to be a result only of waves in classical physics. But strictly speaking, material objects, particles, can generate interference pattern because they have wave nature also. So strictly speaking, this roll of tape, if you take many of those and pass them through slits, the appropriate size and separation, you should be able to see interference pattern. Of course, it is not practically doable because the wavelength associated with macroscopic objects is going to be so small that you can never have a slit with that size or separation between slits with that size. On the other hand, a stream of particles, neutrons usually, but also X-rays, are used in diffraction experiments to figure out the crystal structure of different materials. So if you think about a crystal, the crystal is atoms separated by some distance. In other words, it is atoms separated by a gap. And if you pass X-rays or neutrons or other particles through those gaps between the atoms of the lattice, on the other side, you're going to observe interference pattern, dark and bright spots in appropriate order. From that diffraction pattern on the screen, you can infer the separation, the size of the openings between the atoms. And this is how the structure of the DNA, for example, was first figured out. You get the DNA and you do X-ray diffraction through a sample of DNA. And well, people eventually figured out that it's a double spiral. Of course, there are many practical conditions that have to be satisfied in order for you to be able to do an experiment like this. So let's end it here. And please prepare your questions for from the practice test, from the homework assignments, or from any other source. Prepare them for Monday at noon here in this room. And this is on Wednesday, we're going to have our class. Have a nice weekend.